Did you keep me much today?
Yeah.
I was interested in translating or something. I have already. I'm not saying just 5:45.
I didn't know if they had said anything, so I'm like, well, I'll go ahead and send her a message.
They told me about Friday. Kunden told me about Friday.
Yeah.
What are y'all doing?
Pretty sure.
What are y'all doing?
He's showing them basically his research and stuff. We've been doing so they're doing. He's showing like how they do motion capture on all the spinal patients, and like you get like gait analysis on all that stuff.
Give it just a couple minutes.
Sure.
This is already set up. It's recording.
Okay, okay.
I will be monitoring the Teams chat, or for anyone that might have questions on Teams.
Okay.
I'll let you know. Something like that.
Sure, yeah, that sounds good.
The video streams online, I have it set to where like from here over is kind of like your area. Yeah, the microphone picks up pretty well. For me.
Oh, the microphone's good, or, okay.
All right, everybody. Thank you for coming today to the UofL BE seminar series. We have Dr. Stuart Williams with us today. He's a full professor in the mechanical engineering department. Has collaborated a lot with bioengineering over the years and is here today to talk to you about his intraoperative measurement during spine surgery. So I'll let him have the floor, let him talk more about this. And
Thank you. So I'm presenting this more like a story with respect to some designs that we've encountered and how we've done this along the way. But I'm just one small piece in this bigger project, and we'll get to some of the players that are involved. But with the other faces that are on the screen, at least right now, talking about them, it was, I think it was 2019. Yeah, I think it was 2019, right before the pandemic. Might have been in 2018, but we'll go with 2019, where Dr. Vore sent out, I'm sorry, Dr. Boyachi, the last name on the bottom, sent out an email saying, hey, engineers, whoever's interested, I have a problem and let's talk shop. So, and my background's in fluid mechanics and micro devices. I have nothing to do with surgery, but I thought, okay, I didn't have anything scheduled, let me go downtown and give it a listen. So went down, listened to his idea, and I'll get into all that in a second. But then it was slow going. Talked about with Dr. Vore. We got some ideas, and we have some good momentum right now. And I'll show you everything that's up to date on what we're doing. All the project, I have to give it some name because we're hopefully going to get this licensed out in the near future. The Vertify Probe, and we'll talk about its importance and what it does here. But as you can tell from the pictures, we're going to talk about spine and measuring bone strength But it's not necessarily limited to that. But Dr. Boyachi came in and said, hey, here's where we can help out. But I have to have a caveat in there is that we have one patent filed. We're working on another one. So if you see a cardinal bird covering something in a random spot on a slide, that's why. So there's some things we can't show you at the moment, but there's a lot of things we can. So this will be all redacted. All right. So with that, I want to say thank you for the students, some of them that are here, that really did the grunt work for this. So as one example, at least 1,000 holes have been drilled and tested, if not 2,000 or so. We can probably do the math and figure that out later. But there's a lot of literal probing that happened to this device. But even then, we had to get to that point. So we had to go through different design processes, several 3D prints, some scale, even Amelia shadowed a surgery that Dr. Boyachi did, not to use this device. We're not doing that yet, hopefully soon. But just to get an idea, because it's not just the science of how does this device work, but surgeons need to accept, like, yeah, okay, it works, but if you need to use two hands, you need to balance it just right, the surgeon's going to say, no, thank you, right? And there also has to be a market for it, and I'm going to talk about that as well. So yes, I'm going to focus a lot on the device because that's sort of, I love experimental work, and that's what I'm going to focus on. But I'll also say, hey, here's the market, here's the rationale, here's why this other device didn't work, right? So we're for some of that, but just want to acknowledge all the hardworking students that were there. So we're going to talk about spinal fusion and the hardware that's involved with that. And spinal fusion is the most common spinal surgery in the US, and that involves hardware. And by hardware, we have it pictured. We have a side view on the left, top view on the right. And what we're going to focus our attention on is what's in red here is the pedicle screws. Now, what are pedicle screws? Well, first we have to look at what the pedicle is. So I'm over here on the right now. So the pedicle is that entity, and I'm going to pass around. No, it's on. But it's something you can buy from a company, Sawbones, where they have a cast of one, and I'll get into the details of this exactly. But you'll pass it around, and you're like, oh well, okay. If I'm going to put a screw in the spine to hold hardware to keep the spine straight, there's not too many places you can put a screw, and one of these places is through the pedicle. So you can imagine, and I'll pass this around, that's where someone decided a while ago, we're going to put a screw through this location, and you can't really mess this up, right? Because you have a nerve bundle going right down in that spinal canal, and we can't breach that. But you also need enough meat to hang something to make sure that the hardware is good and does its intended job. So the pedicle screws are coupled with rods to keep the vertebrae fixed. It could be for spinal fusion, it could be for other means, but that is, when we talk about the pedicle, that's where it's at. We're also going to talk about cancellous bone. That's where the spongy portion of the bone and the meat that's in the back. We also have the cortical bone, the hard shell, and both of these play a role in keeping that screw fixed. Now, done that clinical need. When we talk to Dr. Boyachi, what is typically done to figure out what is quality good? In other words, is the screw going to hold? Is there some way we can predict that before we get into surgery? Because surgeons would really like to know all the information they possibly can so they can prepare themselves for a good surgery. It's good for the patient too. So what they sometimes do is what's called a DEXA scan. This is not done the day of. So in other words, if this is situation, you cannot do a DEXA scan. But if this is a preoperative procedure, maybe done a few weeks before, and you get an image like this, think of it like a mild x-ray. So you get this, and then where it's white, it's more dense, and where it's dark, it's less. So you can really identify as an osteoporotic patient or not. You can do that. From this image, can you really tell how strong the bone is? Now, there's a correlation there, but even Dr. Boyachi said that, you know what, this is a lot of the times inaccurate. And he wished there was a better way of measuring the bone strength. Like, yes, this is an image, and it can tell you if it's a bad case. Like, if you're osteoporotic, if you're worse off, like, you'll know. But what about that gray area? What about, is this strong enough to hold that pedicle screw in place? And the conclusion he came to is that the image density, an image like this on the DEXA scan, is not necessarily a strong correlation to bone strength. And also, this is a 2D image. It's a depth average, right? It's not a 3D, like, so there's a lot of complexity here. So on top of that, not just these complications with low quality bone, but our population is aging, right? Those who go through a spinal fusion process is 56 years old on average, and the age is going higher. And as you go higher in age, you are more prone to osteoporosis. And osteoporotic patients have a 50% screw failure. Now, when you hear the phrase failure, don't think that, oh, it just popped out of the back. No. Don't think that. It gets loose. In other words, the hardware only does a good job when it's rigid and holding things in place. As soon as the screw gets loose, then it's not going to be as viable. So one of the pieces of information that the surgeons would need to know is that, okay, great, they're osteoporotic, and sometimes they know this, say, for emergencies. They wouldn't know this until they're actually in there. And similar to those who might have worked a lot of tools or putting screws into different hardware, like a wet piece of drywall versus a firm piece of drywall, you can probably tell, right? And surgeons usually do this by, but even then, does the surgeon need to augment to change, not just put the pedicle screw in, thank you, instead of just putting the screw in, can they have another strategy? Because if they are osteoporotic or they need that additional support, then yes, surgeons could go to plan B or can enhance it. They don't want to if they don't have to, right? They would rather just put it in, have it fit, that's great, but then also have that knowledge that if they need to augment it, and I'll talk about some strategies for that, then they have the tools and that ready and available to attack that as needed. So in the end, is there a way to know the patient's bone quality during surgery and does not rely on a sometimes unreliable DEXA scan? Now, we talked to several companies. So when we had a prototype in place, and this was way before we were in our current step, because we're like, okay, what direction are we going to go? Because these companies, some of these companies are the ones that provide the screws. Think of it like a kit. Like that, okay, here's the screw, and by the way, here's a tool that will help our screws even better than this other company. So think of it as, oh, it's not just a tool that we're going on our own. We really, really, really need the feedback from these other companies in order for this to be successful in the place. So some of their questions to us as we were developing it. So these were the ones on the back of our mind we need to make sure that we address, not just the science, but think of it as the how it's being used. So one, does it add time to the surgery? No one wants that, right? Is it simple? Meaning, can they easily use? Is it better than a DEXA scan? And some of these we can't answer. Like DEXA scan, they'll take a lot of statistics and other things. And then can it predict screw failure? So these are the types of questions that we've got that are on the back of our mind. So as we go through the design process, we have to think about these and make sure that it is really accepted by surgeons. So the industry here, we're going to probably follow up with them with we haven't talked to them in over a year, but at least they gave us some valuable information that, okay, you got to make sure you don't overlook these questions as you go through the design process. So the market itself, let's see, spinal instrumentation, global market, and some of these are older numbers, a few of these, but it gives you a good idea that over $6 billion market from a 2021 figure. And then just the pedicle screws themselves are 724 million. And of the whole bone screw market, because this is pedicle screws, but of course you have screws and hardware for other things. And the screw market is about 2 billion. And in the United States, there is approximately 1.6 million instrumented, meaning hardware is involved, spinal fusions each year in the US, of which over 350,000 are spinal fusions. We estimate that over 1 million screws have been used per year in the US. And currently, there's approximately a 17% revision rate. Revision meaning got to go in and fix it for whatever reason. The screw or some other hardware failed. That's about 60,000 surgeries per year. If a surgery costs about 50,000 each, about $3 billion in the United States each year due to revision surgeries. Now, if they knew the bone quality, will that fix all of these? No, right? There's other complications that go involved. But we did an estimate that even if we reduce this revision by 10%, 10% of that 17%, right? Even if we just conserve and say this, that's 6,000 less surgeries in the United States, and that's $300 million in savings right there. And there's also, in terms of healthcare, there is a shift towards value-based healthcare, meaning the providers work with the hospitals and the physicians, and the payment is being shifted towards outcomes, right? So it's like, oh, if you were gonna, we want there to be less surgeries. I mean, no one wants that, but even from a financial perspective, hospitals are typically foot that bill. And then even the healthcare providers are like, hold on, this hospital over here, you're not doing as good in this area. Why? Right? So there's a lot of questions that come with it. So anything that can help reduce revision surgeries, it helps financially, also helps the hospital out, helps the customer out, is all the above. So there's a lot of benefits to this, financial and otherwise. So let's walk through a typical procedure. So with respect to the current surgical procedure, there are two ways that the hole is created, the pedicle path is created. One is manually using what's called a gear shift probe, and one is using a power drill type method, or another method that deals with robotic surgery. But many use the manual method. So I'll go quickly one slide ahead. This is what a gear shift probe is, and you can imagine, well, why it's called a gear shift probe. It's got a ball and a shaft, and then it has a little curved tip at the end. And what they do there, and if you follow through the diagram on the bottom here. So first off, there's a drill that it clears away the cortical part of the bone. Okay, clears that away. Then they come in and just dig and dig and scoop and dig and sort of just jam and scrape their way in. Now, why it's curved is that they want to feel the cortical bone here where my pointer is as they come in, because they'd rather hug this than the other. And then when they come in, they flip it around and then continue straight. They figure out how deep they go, which they have these notches here that help them figure out how deep they go depending on the screw that they use. And then great, the path is correct. They take that out and then they tap it. Now this is not the screw. This just provides the threads and the path and makes this otherwise, the digging portion of the gear shift probes, makes it straight and ready to accept a screw. So they dig, then they tap. If they do a drill method, similar, and sometimes they can use one or more drills. Some of them are flexible. They still use a little bit by feel, but they drill, and then typically tap, which is not shown in this diagram, and then there's the screw, right? So that's what happens, and we'll go back to this one. So either they have an entry drill that goes to the cortical part, then they go through either a drill or a gear shift probe, and then they tap, and then they insert the pedicle. And then where you see the red there is where we're going to come in. We say, okay, right here at this step where it's red, let's use our vertified probe. And then you can actually, because now they've exposed that cancellous in that pathway. So we thought, okay, if this is just a part of surgery, can we just come in and probe it real quick so then the surgeon knows, oh, wait, this isn't, now they may know by feel. They may know by feel like this is terrible, but what about that gray area, right? So as they come in, they can look at, we can use it to probe it and actually tell them some measure of bone. So the pathway is important. Now we don't deal with the pathway itself, but this is here just as a mechanical engineer that doesn't deal with the surgery at all. We're learning different things about breaches and what's a grade 0 versus a grade 1 versus a grade, you can read the caption there, but it's like, oh, what bad things can happen during this? So yeah, this is all you ideally want what's on the upper left. Then the pictures gradually get worse as you sort of scan through. So the placement is important, but ideally the surgeon has done this in terms of that path that we are going to probe. But I was just throwing this up here more for just for your information, that if it is an aspect to it. Now, when we talked to these companies, they said, okay, well, yeah, make sure that whatever you're working on can help, that is adaptable, because in the future, it's going to be robotic. Now, not robotic in the sense that a robot does the whole thing. Now, maybe that might be something in the way future, but so what they do is that they have a patient has a 3D scan, and then this white covered arm, and it might move up and move down, it will then move this, a drill guide right here that sort of looks like a big metal, I don't know, a tube here that's in that surgeon's left hand. It will position it where it needs to go. And this lip right here where my pointer is, that will stop the drill from going too far. So actually position the path of the drill where it needs to go. And they said, okay, if you're going to do, and also doesn't open up the patient as much, right? So if you can do this, if you can adapt this later for this, keep that in mind, right? So then now we can adapt it for robotic surgeries as well. All right, so that's what's going on in here, but let's talk about pedicle screws. So let's say, okay, what's plan B, or what could be plan B? You can go with a larger screw. You can go with multiple screws, or there's other paths that that I was told that they can take. I won't be able to describe them because I'm ignorant in that area. But also another popular one is over here on the right, cement. There are some screws that are porous that once you put the pedicle screw in place, you put in bone cement and it fills in the cavity and then makes it more rigid. That's fine. But the reason then some people are like, well, why don't you just do that all the time? If there's any of the breaches that we talked about on the previous slide, guess where that cement's going, right? Not where it's intended. So that's one of the reasons why they want to avoid that, just in case. So keep it simple. If it can just be a threaded standard anchor, great. Otherwise, there's all these different shapes and sizes, and I just pulled this from literature. I haven't worked with any of these others at all, but there's methods that can be used to that if a standard screw doesn't work, there's things that can be done. With respect to the tap, there's a typically accepted rule based on a 1993 study that when they tap, that we talked about, when they tap that path and then they put a screw in, it's usually not an identical match with respect to diameter. The tap is usually 1 millimeter smaller than the screw, which that makes sense if you think about it. But that was just based off of studies, so a lot of surgeons use that rule as they go forward. Some people have asked, well, what about torque? The torque as you apply the screw in, could that be a measure? Studies have shown that there's no correlation. So the torque that is puts in versus if it's going to fail, that's something we even consider, like, oh yeah, why don't you just make the torque in? Now some studies say no, that's not a good way. So now we're into what is the Vertify probe itself. It's a medical device used to measure bone strength to get an idea of what part within the surgery that we do it. And then sometimes when these screws get loose, like they toggle it. And in some x-rays, what's in red here, of course, the x-ray is not going to be red, that'd be more of a darker area. And that you can actually see it where it would have withered during this process. So it's not an implantable device. We probe it, measure it, done. We don't believe any clinical trials are needed, at least at this point. So when we go through some testing, we just need an FDA class 2 for this. And then it's non-destructive. And we also say there's no additional drilling needed. You already did it. So after it's tapped, we're ready to probe it and see what we can get. So what have we done? We've done, we did a true scale design. We did have a larger scale design. We 3D printed a lot of stuff out of plastic to see what would work. We got some surgeon feedback. We went through that. We tested a lot, and we're still doing that. And then we've most recently got cadaver specimen. We got their DEXA scans. We're about to probe them. We're going to actually do their toggle tests. We're sort of on the end of phase 3, beginning phase 4. We're in talks with some companies to figure out how it's going to be mass manufactured. So when we talk to others, hey, this is how much it's going to cost you. We're going to get those reports ready, and then also some FDA discussions as well. So we are really close, but really all this part up to this is a lot of testing, which is what I'm going to go through here very soon. But at least you have the bigger picture of where we're trying to go. This was our first design. And what we thought was, okay, let's have, and I'm going to describe it. We have this probe here, and there's a cantilever right here. So there's a space. So this outside space, it can deflect up, and I showed it deflecting up here. And it can deflect up when the shaft is entered inside. So this shaft goes in here. As it moves along, you're putting a torque on it. As the shaft goes in, it pushes this cantilever up, and that cantilever pushes against the cancellous bone, which is when it's inside the patient. And we thought, okay, great, this works. And it does work. However, when we showed this to a surgeon, they didn't like it. Well, why? Well, the reason is you have a torque sensor, so you have one hand working the torque, but nothing's holding this end. So now you're using two hands. And they said, can you have one hand operation? We're like, maybe. We went back to the drawing board. So there's other reasons too. Some dealing with manufacturing, but we're like, okay, let's not do two-handed approach anymore. Even though based on our 3D printing and stuff, the premise worked. So then we had a second generation. So our second generation design was that, okay, we have our cantilever, but the hole that is here was generated by the tap. We designed this cantilever to fit that tap, and then here's a cross section of two foam blocks of different compressive strengths. And that cantilever, this little extrusion down here, that would come in contact with that underlying cancellous bone, or foam in this case. And then depending on how strong it is, it's going to push it up, and the angle is going to change. So we would have a strain gauge right here, and then it would measure the amount of strain on that strain gauge, and therefore deflection, and therefore make that deflection correlate back to the strength of what's inside. So that's what that's what our idea was here. So then it gives you an idea of, okay, here's the probe, here it's strained, there's a resistive force due to the bone, and then here's where we sort of envision everything that's happening there. And there'll be some indicator on the dial itself. We could do some Bluetooth, we could do some wireless, but we thought that was trivial. Like, let's worry about that later. Let's actually get it to work first, and then we can make everything nice and polished and have all the bells and whistles later. Here's a example with this. So we have a 3D printed plastic probe here with a gauge. This is the very cheap scale indicator. They use this for like food weighing scales. Just got that. It converts that strain, and you can get this is a strain measurement here, and we tested different block compressive strengths and got reading, and it plateaued because you can only have so much deflection, right? There's going to be a maximum. So now there's some mechanics involved with the cantilever equation and tweaking that and doing a lot of tests and all that stuff. But in the end, the electronics themselves are inexpensive. So we were even debating, could we just throw away, have it a one use? Use it, throw it away. Use it, throw it away. Could we do that? Or do we need to sterilize everything? Do we need to sterilize electronics? And these are still conversations we're having. So we're still trying, and that's where when we talk to a manufacturer, they're going to help guide us down this path and figure out, should we reuse it? Should we have it as a single use and throw it away? Those types of things. But in the end, on the handle, we're going to have, we thought we were going to have a digital display, but the surgeon's like, I'm not going to read it during surgery. Just give me a color. That's it. That's all we want. Okay, fine. Like, we'll still record it, and we can upload it to a computer later and do some like R&D and all that stuff. But the surgeon's just like, no, just give me a color and make it really bright, because I'm not going to stare. I'm going to stare at other things. So okay, that's fine. So if I can catch the color out of the corner of my eye, that's great. I'll still look at it for sure, but make it obvious. So now we would have a video of this, but it didn't work. We tested it right before. So with our newest design, that you can see why it's going to be so well, because there's a cardinal bird right over it. So with that, we have an LED here. We have two buttons, and we're going to reduce this probably to one button later. But with this is a ultra bright LED. Will change its color based on, and right now we have 3 colors. Could we do other things? Sure, but we're trying to keep it simple. Green meaning good, red meaning bad, yellow meaning be careful. So based on a strain that we decide, and we'll get into, we've had this question many times, what's a good number? What is green? How do you know good and red is, but we'll get to that. But at least the premise is, okay, here's the device, here's the handle. It can be battery operated. I know we have wires coming back out here, but that's just for us keeping a consistent power and even collecting more data. But it can all be portable. And all the electronics that are here are cheap, right? So that's where that we're again debating whether that should just be disposable or not. All right, so how did we test this? A bunch of foam blocks. So when we assemble it, we're doing this by hand. And for those who've ever worked with strain gauges or mounting sensors, there's going to be some inherent variability since we're doing this by hand in terms of the gauge can be mounted 0.5 millimeter to the left or to the right, which means we have to calibrate each one that is assembled, which means we have to have a series of holes in different blocks for each one that is assembled. Sorry, you all did all the work. Thank you, Owen. But they did all this literal probing, collecting of data, assembling stuff. But there is a company, Sawbones, which passed around. They have a series of blocks that they consider, this is representative of a series of cancellous bone strengths. So we're able to probe it and figure out, oh, for 2 megapascals, here's our reading. At 4 megapascals, here's our reading, et cetera, et cetera, et cetera. We also have blocks from General Plastics, who we found out they were the suppliers to Sawbones, meaning we could get it cheaper. But they also made a wide variety of plastics, not just, it seemed like Sawbones had their own type. And we even tested different types and said, wait a minute, even though this is 4 megapascal and this is 4 megapascal, they were manufactured different and the compressibility was a little. So in the end, we are now more familiar with foam than we wanted to be. But we acquired measurements from our Sawbones blocks. From that, because we want a consistent supply or a consistent type of foam that was manufactured, from that we then created a calibration curve for each one of the probes. Then we tested against the General Plastics, which was a different value, because we didn't want to test the value we calibrated at, because I mean, it makes things really, really easy for us. So we actually wanted to have a value that was between these calibrations. So I'll show you our calibration or a calibration curve in a moment. But then we would test it in the General Plastics and we would compare our measured based on the prior calibration to the actual to see where we're at. So here are on the left, the Sawbones, the product numbers you can don't have to worry about. And then the compressive strengths of the different ones from Sawbones that we got. So those are the ones that we're going to get our calibration curve from. And General is the ones we tested it against. Now, is it the exact same foam? No, right? We did that on purpose, right? Because if we went back and tested one of these, well, of course, we calibrated around it like we're going to be really on target. We want to make it, we will make it hard on us. All right, so that's why we did this. Here's an example calibration curve of probe number 1. I forget, there's at least 10 holes for each of these points, if not more. Is that about?
10 holes, 100 average of 100 measurements taken from each.
Okay, so yeah, so 10 measurements per hole, 10 holes. So this is our calibration curve, and it's not as we would like it to be. But it was fairly consistent. Like this one maybe dips down a bit, and it's not linear. We weren't expecting linear. But for those who are even thinking about like how a cantilever bends, like we'd get a sharp and then sort of reaching a plateau, if you will. So we were expecting a little bit of a different curve just from basic cantilever mechanics, but classical problem. This isn't a single point load. And even the distribution, like how it's interacting and how it's bending, is changing dynamically. But it is what it is. Right, and we were expecting we wanted to be sensitive. We were expecting that that a good bone quality would be somewhere in the realm of 5 to 10 megapascals. So we thought, okay, we want to make sure that there is we can differentiate that, especially if it's weaker bone. Like once the surgeon knows it's weak bone, they can use that however they want. But yeah, so digital reading, arbitrary value on the vertical scale, and then horizontal is all the foam compressive strength there. So there's our calibration curve for a particular probe. And we compared it to the general plastics. And you can look at the data and say, oh, you're 20% off. Yeah, I mean, but does the surgeon, and this, we may not be able to answer, we can't answer this question right now, but in the future, is this good enough? Like, is this even better than DEXA scan? We're not trying to hone in on, oh, we have to get within 1/10 of a megapascal. No. We cross a line. Is it good or is it bad? That's really all that we're looking for. So you may look at this and say, oh yeah, about a 20% error in an experiment. That sounds like a bad experiment. Well, is it? And those are questions that we need to ask ourselves as we move forward. But we also tried to make this as difficult for us as possible. And if we have time at the end, I can dive deep and go into some details about why we think we have this error, or as significant as some people may think. But I will look at this and say, well, if we're just trying to figure out where's our cutoff point, and are you below that or are you not? And then maybe this is sufficient. Maybe as you go higher in megapascals, that we can tell, oh, are you below 5 megapascals? Here you go, right? The exact value doesn't matter. Is it weak or is it strong? Is the question we're trying to answer. All right, so this is those are results from that. Now repeatability. We had 4 different probes for this graph, 4 different calibration curves, meaning all that testing that was described before, we do it 4 times. So probe number 1 is shown here, but also probe number 2 and probe number 3 and probe number 4. So when we had these manufactured, we tested them, strain gauges manually placed, calibration curves applied, done all this, and it seems that there's some change here and there, but somewhat consistent. So that's good, right? So it means that we're on the right track there. We also had 3 student users with the same probe. So what if user number 1 had a more shaky hand or whatever? So they all had the same general instructions, and said, okay, probe these 3 blocks and let's see how different you all are. Again, these results are promising, right? We should get more users and actually get surgeons and not students to do it. But again, these are promising results here. Now then it comes back to, well, what's a good value? What's a good compressive strength? And this is sort of where we're shifting gears to a different mechanism. So Dr. Vore, he has a methodology that's been published where he will take a specimen. Now he's also done this with cadaver specimen as well, but we're going to our foam blocks. So we have a foam block, and it's in this MTS machine, applies a load, and this special jig here, and you can see that jig right here, sort of 3-dimensional view. That's as we're applying an oscillatory load, right? Every second, applying a load, and we keep on increasing the load and increasing the load, and then monitor the deflection here. This simulates a rod on that pedicle screw that is in this foam block, and then when does it fail, right? Based on the loads that, and if you ask me, oh, are these loads appropriate or was it mimicked on, I would just say, let's talk to Dr. Vore, who's not here. But at least, and as a publication, I can share with you and connect you with him. But either way, mimics a biological load that keeps on increasing until it fails. So this is an example using a 1 megapascal foam block, and you start, the displacement is on the left, or I'm sorry, on the vertical, and then the horizontal is just number of cycles. Boom, boom, boom. Does 100 cycles, and then ups at 20 newtons. Another 100 cycles, and that's why you see a low, high level of displacement, because it applies it and lets go, applies it and lets go, applies it and lets go. And then once you get this discontinuous sort of slope here, and it's not as horizontal, that's when we said failure, right? It's not that it comes back. It comes back to normal each time, okay. But as soon as it deviates from that, that's when it crosses the line of failure, and we're okay. So in this case, the 1.5 megapascal failed around 220, 240 newtons with this cyclical loading. So we only went up to 300 newtons with this cyclical loading because Dr. Vore didn't think it should be above that based on his experience. And now, is a linear fit appropriate? I don't know, but we have 3 data points that we know their failure. The 4th one, this was a 9 megapascal. It survived the 300. So even though this data point is here, it didn't fail. It's somewhere, who knows where, but it survived. It survived. So we know that 4.9 megapascals is good for this test, and it didn't fail, but all these others failed. So in other words, when do you cross that line? Maybe it's somewhere between 3.2 4.9 megapascals of what is good and what is bad. So this helps us determine that red light, that yellow light, that green light, what are those values? So we're still continuing tests with different foam blocks and stuff. We're still collecting data here, but at least this gives us some idea of, okay, based on these biological loads, what is a good compressor for this cyclical load? And this just helps us with that information here. We've done some other things. This didn't work out. It was neat, but it didn't really work out. So we tried to look in literature because we had a tough time getting a cadaver specimen, and we still are. We only got 1 specimen, so I hate to put all our data in just 1 specimen. So we're like, okay, is there any animal bone out there that has the cancellous bone that we think it could work? And we dug in literature and said that, oh yeah, the greater trochanter of the femur up here should work based on literature. Now, most of the time, yeah, a clear majority of the time, animal bones are going to have higher cancellous bones just because just the nature of how their biomechanics. So we're find, oh yeah, let's find softer cancellous bone and big enough to put a screw in. Where can we find this? So we've dug in literature and found this. Okay, great. So made friends with Trackside Butcher Shop, and they gave us some bovine femurs. At least the head of it. The rest they would sell off and things like that. But up there, we said, okay, can we have this? Okay, gave us a few. But even then, could we probe it? Yes. The holes that are shown on the right here, these 3, even though we chopped up a block, you cannot say that all 3 of those are going to be the same value. It's inhomogeneous. So in other words, okay, great. Well, what's its actual value? Now we know what its neighbors is, but it might have a little fatty. It might have a fatty pocket or something. So it was an attempt, and we could take measurements, but in the end, did we actually know what the true value was? No, and that's where the value of those foam blocks are, is that they can help us really hone in and target what we want. Sawbones. So the sample that was passed around, just like they make big foam blocks of different strengths, the interior foam, so the cortical is this shell. But the cancellous on the interior, they have them at different densities. Now we haven't done it yet, or well, we did do it. You see some here, but we had to make a bigger hole than necessary because our probe wasn't long enough. So we're going to repeat these, but with our new probe that you didn't see. But we're going to repeat these and then actually measure a known foam value and see if we can actually get a result from that. And then also we're going to toggle test these and figure out when they fail. And then the cadaver specimen that we have, we're going to take a DEXA scan of it, probe it, and toggle it, and just do the gamut of tests in that order. Just so we know the DEXA scan value, we know our probed value, and we know the value at which we're going to do it with the cadaver specimen, and we're going to do it with the sawbone specimen. That is what's on tap, I guess, next. So we do have a longer probe that's going to help us with all of these things. I just talked about what we're going to do with the cadaver and the sawbones. We also want to get a surgeon, like get in the cadaver lab and say, hey, here's a probe, use it, right? Give us feedback, user friendliness, things like that. And then with all this data, we're going to go back to companies and say, okay, what do you think about us now? Like what's good here? And go from there, because ultimately we want them to use it to talk to their hospitals and say, hey, hospitals, you should use us. Our screws are better. Not only is it better, we now have a tool here to help patient outcomes, right? And that's just something they would like to hear. So with that, I'll wrap up. But this is a means to target bone strength It's non-destructive. There is even some tactile feedback with this probe as well, that surgeons generally like tactile feedback as well. But in the end, we want this to where surgeons can make better decisions and give them as much information as we can and really save hospital cost of revision surgeries and have better patient outcomes. With that, that's it. Thank you for your time. Questions?
So I know DEXA scans are pretty limited. I work in peds, so that's a big issue for us. But CT scans can provide a lot of information, especially related bone strength. Have you considered, like for the bovine testing, doing 3D scans as well to be able to get a better idea of bone strength and how that correlates to your device?
You are absolutely right. The CT, there have been some surgeons that come to us that, or there was one in particular that comes to mind that said that, oh yeah, DEXA scans, we think they're going away and we think they're going to replace with CT. And I do believe, just based on where CT has come from, we believe that will be a better scan than DEXA. However,
You can't do that intraoperatively.
yeah, and also it goes back to the question of what is the, can you predict strength? Just like can you predict strength from DEXA? I bet you the CT scan would predict it better, but is that still better than maybe our probe? That's a question that we don't know. But would CT scans be better? Yes, but can CT scans predict strength? You have an image of how density is density the same as strength?
There's high correlations
There
in the
is.
literature, especially for vertebral collagen, is pretty heavily studied for that. Or at least like for people who aren't aware, a lot of automotive study is very focused on vertebral injuries. So a lot of that's been characterized for those FEAs because they use simulation pretty heavily for those accidents. Sorry.
No, that's perfect. No, and I do agree that CT scans are likely better than the next. I'm sure there's papers.
Have you considered incorporating that into like validating your kind of like good, bad, medium?
I think that would be valid. We chose DEXA because we were told that's the standard, so let's run with the standard. But we are into like other comparative measures as well, especially if it's straightforward. Like, oh, let's do a DEXA scan, let's do a CT scan, now let's do our this as well.
I was just thinking with the bovine femur, if you did like a comparison of a CT scan and did an FE study and see if you could match experimental results, and then if you could do that with
That's a good idea. We have not considered that, but I think that's instead of, yeah, but in the end, it's true strength. But at least that would be a better correlation to what we're doing now.
Well,
Absolutely.
especially you would need to really for those get micro CT scans because, like you're saying, the limitation with DEXA and then less so for CT is the resolution, especially with cancellous bone. It's so fine.
Absolutely. Yeah, you're right. You're right. And those are some good thoughts.
Sorry.
No. Thank you. Sure.
So has there been any thought about, well, maybe first of all, when you put this probe in, the reason the cantilever is deflecting more in harder bone or stronger bone is because you're able to push it back some more. Is there any concern about damaging the threads or the bone?
Absolutely right.
Softer bones?
Let me. So you can't see what's going on, but you can see on the back end. So what I want to get at is that you're right, that as the cantilever, so first off, there's threads here, so there's pockets,
Right.
which could potentially disrupt, and that's one of the reasons why we think that error could be there, is our clock of our thread and where it's contacting exactly the same every single time.
Oh, right.
But to your point, because it's related to this, is that when they tap that 1 millimeter rule that they use, put in the screw, you're compressing it anyway, the cancellous bone.
Okay.
Our cantilever is also, let's say, compressing it, but we also purposefully designed the pad here, as you cannot see, that we designed its interaction such that it doesn't do any worse compression than what the screw's going to do anyway.
Yeah.
But you're right, like what if, aren't you just making the hole bigger by scraping everything about it? Well, if you're going to put the screw in the same spot, we're doing the same amount.
Sort of another question with the doctor said they wanted Has there been any thought about giving the doctors the ability to set what those thresholds are? And this is just a total guess on my part, but is there a possibility that like they would consider a bone to be hard enough, say, in an older patient who's not going to need this thing to last for so long as in a younger patient who might need this for another 30, 40 years. They might want that threshold to be a little higher for a younger patient.
So you're getting at a very interesting topic there in terms of like targeted, like, oh, based on maybe their weight, their lifestyle, their age, all the above, and say, oh, wait, their goal is this or that or whatever it may be. I don't see why we couldn't, like, because once you have that calibration curve, I don't see why you couldn't dial it in. Now, what those numbers would be, I don't know, but to your point, you could say, you know what, for this application, for this recovery, whatever it may be, maybe they want to be more conservative, maybe they would be more cautious, and or maybe not. So maybe they can dial in based on the circumstance. I don't see why you couldn't, and maybe have an interface like we've had. Oh yeah, let's have a display over here but the surgeon we talked to is like, just now keep it simple. Like you don't want to add more training or more buttons or more noises in front of the surgeon than you have to. But is that a possibility? I don't see why not. Yeah, that's a good point. Yeah. Unless there's other.
Yes.
Yes.
Yeah, I just had two questions. So the first question is, so do you have different sizes for different size holes or whatever? Is that all part of the tool, or is it going to be like an adapter you put on and you can adapt the size?
What we were thinking is, because the current kit that you get from the pedicle screw providers is that you get taps for different sizes, and usually the surgeon or at least has a plan for what screw they're going to use anyway. Now, can plans change? Yes. Oh wait, we got to go bigger. They're more osteoporotic. Let's bite into that a little bit more. So we were thinking that we would have a different probe, and these could be either swappable, or since electronics are so cheap, just like you have a kit of different taps, you'll have a kit of different probes ready to go. So either the probe would be swappable with a handle, or maybe everything's cheap and you just have all these ready to go. You can just pull out, just like a screwdriver, like, oh, I need, or a socket wrench, like, I need this size, oh, I need this size. You can just pull it and go. This was a thought that we had. But you are right that there's different screws for different applications, and our probe does match a tap that is used, which is why we have to match ourselves up with the hardware companies.
Tap size right now.
Yep.
That would be, and my second question was, for the way the cantilever works, it needs to be very coaxial, right, with the bone. So do you know the variability when after they drill? Because being at home, putting a drill into a hole in the wall, it's sometimes there's do you know the variability there at all?
That we have not looked into, like, we didn't find any literature that said, oh yeah, here's, like, we'll say the picture that's up here, like this entry point here, like we assume that it's snug on the back end in order for the front end to work well. What happens if that back end is bad? Also say, well, wait a minute, they're going to put a screw in that same hole. So to answer your question, no, I don't know. Would it influence it? Absolutely. But also, it would give a weaker reading. But would that mean you're setting up your screw to fail anyway? So there's, I can spin that to be a benefit, but at the same time, it's a good open-ended question.
I mean, like a use case for them. So if they put it in and it's wiggling, they're not going to need the right.
Yeah, and as we dive down, like as we converge to an appropriate design, we can drill even more holes and 1,000 more holes and figure out, like, oh, and what if we drilled it a 1/10 of a millimeter bigger? What would happen? And we could definitely dive down that hole if we had to. Thank you. Yep, you're good. Yes.
With respect to the robot, potentially, I realize it's pretty far down the line, so I don't know how much you guys have thought much about it at this point. You said that they plan on doing a 3D scan for it. Do you know what type of scan that is?
Oh, I need to look that up. Well, there's a journal article where I got it from. I'm trying to remember what they did exactly, and also they scan, like they do it while the patient's already sedated and down, because if they move,
Right.
yeah, that's it. but at least this is the process, because we were looking more at, oh, what drill do you use? How long is it? Oh, do we have to make our device now
Right.
much, much longer? Thinking it from that end, but how they sedate and how they image, I would say look at that article, and if you can't find it, let me know. I might have another
Well,
article.
just because I was thinking like if CT is the future and if that's what's being used, then would it end up making your device kind of not inconsequential, but like less relevant in that respect, depending on what type of imaging they're using? Although the second part, follow up to this, sorry, was are you kind of seeing it more as a tool for replacing human touch for like doctors that like are doing it, so the robot is feeling it instead? And then if so, are you planning on doing studies potentially tying like what is a kind of like rating versus the actual device's rating?
We want, so putting the robot aside, we wanted that tactile feedback. And even as students can say, oh, when we put the probe into foam, like we have like some very strong foam. We're like, I can't take it. Like it's like we exceeded even what Cancellus would do. There is that tactile feedback when you actually use it, and based on what the surgeon, some foam blocks in front of him, he liked that. Now, getting the robot into play, it still seems like there's a drill, so it seems like there's still some tactile feedback. But if the surgeon is not actually digging with a gear shift probe, or like there is going to be some loss along the way. And whether, and the CT scan that you mentioned earlier, could, if the literature does show, like you said, that the CT scan is likely better than DEXA, but is that still better than what this could be? Don't know.
Well, I guess my question more is like from a robot perspective, if like when you said the manual's the most common method, I think, for using it, they can kind of like tell some degree of like the bone quality going in, because when you're digging it, like is it looser, harder, or something?
Yep.
So is that like correlation of touch going to be similar to the type of readings and feedback that you're getting on there? And then can you, like, obviously bone quality is the most important, but like, will those still correspond to like how surgeons are doing it now? And then that could also be a marketing tool saying like, you're not actually reading these as well as you think you are. That's a high failure.
Yeah.
Sorry.
No, these are, and we can't answer that, but those are very good thoughts in terms of like all the above, the surgeon experience, whether you put that under that umbrella, like in terms of versus experience versus skill. I mean, surgeons are gifted. Like they have a lot of great intuition. We're not saying we don't want to replace this, but just sort of like we want, if there's a gray area, right? Like if it's obviously good or obviously bad, they can probably definitely tell by feel. But what if like we just sort of want to raise a flag to them? And that's really all we're going to do with these fights, is we're just raising a flag to say, hey, are you sure? Right? It's still, the decision's up to them. But could this help them? And those are just questions that we're looking forward to answering.
Cool work.
Any other questions? I don't think anybody has any. All right. Thank you for your.
Thank you.
The micro CT might be something that's useful as well with
I
if you're
agree.
doing bone section, just to see where the probe is hitting, and then being able to tell does that like influence.
And with the ones that use there's some surgeons that use drill and no tap at all. Like if they use the